is bounded between -1 and 1, so it's impossible. So this can't possibly be 2, right? So there'd be no answer for this. This wouldn't make any sense. But if you put 2, you would be incorrect. All right, so that's the dangerous part of that one. This one is even more dangerous. So let me show you one simple usage or simple application of sine inverse of sine of pi over 3. That should be pi over 3. Because what's sine of pi over 3? Root 3 over 2. Right? We just did that. And then now the inverse says, OK, go back and tell me what angle you got this from. And that's going to be pi over 3. Can someone give me an example of one that would not work this way? Sine inverse sine of pi? Is that what I heard? Pi? Is that just pi? Well, if you don't pay attention to it, yes, you'll think that's what it is, and it's incorrect. Because what is sine of pi? 0. So you're really saying, what's arc sine of 0? And so now this is, all right, where on the unit circle is your y coordinate 0, right? That happens here and here. But wait a minute, we're looking at an inverse. We have to cut these off. So your answer has to be 0, doesn't it? The angle 0. So this is 0, not pi. Just be careful with the cancellation property. All right, now we're finally at the derivatives. All right. So what are the derivatives of these inverse trig functions? We know that we can graph them, and therefore they should have nice tangent lines somewhere. So let's figure out what it is. There should be 6 of them, right?
Yeah.
To do this, we will have to use a couple of things from the past. Reference triangles and implicit differentiation, which is why I gave you that warm-up that I gave you. So let's try and find, I'm doing example 2 here, if y is equal to the inverse sine of x, I want us to find y prime. I'm going to do this one myself, and the next one I'm going to ask you to do. All right? See if you can follow this. First of all, I cannot just take the derivative on both sides. I can't just say, OK, y prime equals the derivative of this, because I don't know what the derivative of this is. Can I bring the -1 down? And no, because that's not a power, right? This represents an inverse function. So there's no rule that we have that we're going to be able to do to deal with this. So what we do instead is we get rid of this inverse part by applying the sine function on both sides of the equation. Okay, so I'm going to take sine on both sides of the equation. Does that seem like a legitimate move to you, like an algebraic move? Does that seem OK to you if I do that? Okay. Now, there are some certain restrictions now. I mean, we do have restrictions on x, because we know that there are domain restrictions for x, right? But what that allows me to say now is that sine of y is equal to what?
Sine of x? Or x. Yeah.
Sine of arc sine of x, which should be x, as long as what? Well, go back up. What was the restriction we had for this one? As long as the x was between -1 and 1, right? So this is true if x is between -1 and 1. Right? So we're all still good with that? Now, what's the value of me doing that? I mean, what have I gained now?
You can do a chain rule.
Now I can do a derivative, right? Because I know derivative of sine. And so what I'll do is implicit differentiation at this point. Right? So this is a big point in the problem that this is not the answer. I'm just boxing it because we have converted something we didn't know the derivative of to an equation that has things that we can take the derivative of. So let's take derivative implicitly with respect to x, and I'll do it up here. What is the derivative of sine of y? cosine y times y prime, right? So we have to remember that chain rule. And then equals, what's the derivative of the right side? 1, right? Because we're differentiating with respect to x. And what were we trying to find? Y prime. There it is. Isolate it. Divide by cosine y. Yes? The only problem with this so far is that most of the time in Cal 1, if you have y as a function of x, and you took the derivative, your answer was in terms of x, wasn't it? Like if I gave you y is equal to x squared plus 1, asked you to take the derivative you would have said was 2x, right? So x was in the answer. Here, the answer involves y, not x. So what we'd like to do is get that y back to an x.
So you're
Right.
right. 17 million.
We could replace that y with this right here. We could. Do y'all see that? I could write this. Don't write it though, okay? We're going to do something else. Would you agree that I could do this? And that would be it?
Yeah.
Yes? Okay, but we're not going to. We're going to do something a little different. We're going to try and figure out what cosine y is. And I'm going to go back to this thing that I boxed. And I'm going to draw a reference triangle. So what I'm asking you to do right now is draw a triangle that illustrates this equation. So here it comes. Here's a right triangle. The angle in this equation is what? Well, that is, right? But what's the angle in this equation? The x or the y? The y, right? So I'm going to put a y right here. Do you agree that that triangle has an angle y in it? And according to this, sine of y has to be x, which is the same as saying sine of y has to be x over 1. And when you're dealing with trig functions, sine is which side of the triangle divided by which side of the triangle? Opposite over hypotenuse. So the side opposite of this y should be what? X. And the side that is the hypotenuse should be 1. Yes? So that picture goes with this equation. You need to be able to do this a lot in this class. So comfortable with that? Now, what is it that we wanted to know? What is cosine of y? That's adjacent over hypotenuse. Do you know the adjacent side? You can solve for it, right? You don't know it right now, but you have 2 of 3 sides of a right triangle. So we can find this adjacent side? Let's call it A for adjacent. How about that? Let's find what the A is. So a squared plus x squared is 1 squared, which is 1. And so a squared equals 1 minus x squared. I'm just isolating the a squared, moving the x squared to the other side. Finally, square root. Do we need plus or minus? No. We're assuming a is a positive length of the side of a right triangle. So that's a. I'm going to come back in here. I'm going to just replace it. What we want is 1 over cosine of y, which is the same as secant y. So you could just do adjacent over hypotenuse. No? No, that's cosine, sorry. Hypotenuse over adjacent is secant. Yes? Okay, so our answer should be this over this. So y prime should be 1 over square root 1 minus x squared, so long as the x was between -1 and 1. That's it. That's the derivative. That is the slope of the tangent line. Can anyone see that as long as your x is in the window -1, 1, does everyone see that this derivative is always positive? The numerator is always positive, right? 1 minus a number squared, as long as this number is between -1 and 1, when you square it, it's going to be smaller than 1. So this will give you a positive number always. The square root of a positive number will be a positive number, which means that the derivative is always positive, means the function is always increasing, isn't it? And we showed it up there a little while ago that it was increasing. All right, so I'm going to give you a couple of minutes. Let's see how much further we have here. I talked a little more than I wanted to. You know, I'm going to keep going. I'm not going to let you do one on your own. Sorry. I was going to let you do cosine. So now we know we have a general formula for the derivative of arc sine, right? There it is, right there. But now, right away, we start applying the chain rule, all the rules that we can do with this. So on the next example, we have find the derivative with respect to x of, I want to change this problem up a little bit. Make it, instead of x squared plus 1, let's do 2x squared minus 1. All right, so me doing that thing with the reference triangle and figuring out what the derivative of arc sine is, that's a one-time thing. We don't have to show that ever again. We have a formula for it, right? Now we use the formula for something like this. So we're trying to take the derivative of arc sine of something, right? So we're going to need to apply a chain rule here. The outer function being what? What's the outer function here? The arc sine. The inner function being the 2x minus 1. So again, depending on your Cal 1 experience and how good that was and how the chain rule was, let's see if you can determine this, what this would be. So what's the derivative of arc sine of something here? 1 over the square root of 1 minus x, but x in this problem is not x. It's what? 2x squared minus 1. So that goes here. I'll do it in a different color. 2x squared minus 1, but then squared, right? So that's the formula we just came up with. 1 over the square root of 1 minus x squared. Then chain rule times the derivative of what's in here. Well, that should be clean, right? 4x. That's it, right? And we could clean it up. We put the 4x on top. We could expand this out and, nah, just leave it. This is good enough.
And that's how you want it for the rest of the year. You don't need us to clean up, as it were.
This doesn't have much that we would clean. Just the 4 on top. Yeah, that's okay. Yeah. Yeah, this is not like with the Cal one where you had to simplify the derivatives and make them look better, although you will be wishing that's what you were doing again at some point in time, probably.
Do you worry about rationalized radicals?
No, I don't.
Okay.
Yeah. When you're talking, yeah, no, I'm not. But that's a different conversation. I'm sure I will get to it at some point of why I don't look at it as, I have a different perspective on it, I guess. All right, next one. All right, that was, I gave you the derivative of arc sine, right? The others can be found in the book. And they're on your formula sheets that you're allowed to print and bring to class. All right, so don't get caught out next class. I give some pop quiz over what are the derivatives of the inverse trig functions, and you're that one person that didn't bring the formula sheets, right? Because that would be a gimme quiz, wouldn't it?
Right.
Yeah, so you're responsible for knowing what they are. Anybody have their formula sheets with them? Yeah? So what's derivative of arc cosine? Can you find it on there?
Yeah. It
It's the same as the arc sine derivative, but it's negative 1 over that. And then there's arc tangent and so on and so forth. Arc tangent's worth us mentioning, though. I will mention this one. If y is equal to the arc tangent of x, the derivative of this, without me showing you the whole process, is 1 over 1 plus x squared. But you could do this exactly the same as I did the other one. You would take what on both sides first? Tangent first, then you would do derivative, then you would do a reference triangle, and you would eventually get back to this. This will be with us until the end of class. This will never go away, the derivative of arc tangent. So maybe a star next to this one because it does come up so much. So I have another example that has some chain rule in it. If y is equal to the square root of the natural log of arctangent x. I'm asking for the derivative. I'll give you like 2 minutes to see if you can do that on your own. It was good, man. It was good. I was ready to come back though.
Okay, let me see.
Yeah, it was good, but
Holidays? Change your money? The holidays change your money?
if I want to go buy something every day, you know. That's the way it is. But
Yeah, I don't think I'm leaving for that 2 weeks thing.
okay.
Remember I told you about last
Yeah, yeah.
I talked to him and let me stay.
Oh, good.
And then I'm like, I'm gonna do it in the summer.
Okay. All right, you get anywhere with this? How many of you think you have it? Show of hands. All right, so if you're going to use chain rule here, how many kind of layers to this onion do we have?
4 or 5. 3.
What would be the outer function? The root. Next one in? Natural log. Next one in? Arctan. So maybe like 3 layers to this. So you start by looking at what's the derivative of the square root of an expression. So what is the derivative of the square root of an expression? 1/2 square. Okay, so depending again, this is Cal 1, how you learned it. The derivative of the square root of something will always look like that. Okay, always. Now some of you might do this, and then up to the negative 1/2. That's correct also, but if you were to clean it up, it would wind up looking like this. But what goes in here?
Natural log.
Everything that was under here, right? Natural log arctan x. All right, now chain rule, some multiplication. Now you move into the next function. We've taken care of the square root, so times derivative of natural log of something is 1 over it, right? So 1 over arctan x. And then times again. Now the derivative of arctan x, which is 1 over 1 plus x squared. You could also write x squared plus 1 on the bottoms, which doesn't matter. Is that all right? You can't bring arctangent up, right? and say that this is just tangent? All right. It's one of the places in math that really mathematicians should be ashamed of themselves for using bad notation here, right? Because in some sense, sometimes that means that power, a negative exponent, and sometimes it means an inverse. And they're totally different things. So you have to know in the context of how it appears. So that would be it. You could, again, push this all together, make a 1 on top, maybe put the 2, maybe the arctangent right here. You can maybe put that out there in front in parentheses. But that's it. That's your derivative. Just trying to get you to think chain rule. All right, let's try this next one. How about this? Arc sine of xy squared equals 1 plus x times y. And you're asked to find dy dx. So can we find the slope of the tangent line, some way of representing that if we have this equation? So anyone recognize what we're going to have to do here? Implicit, right? I mean, there's no way around that. You're not going to be able to solve for y. And so let's go after it. How about the left-hand side? You're going to be taking the derivative of arc sine of something. And we just came up with a formula for that. So it's going to be 1 over the square root of 1 minus this. What do you call the thing that lives inside of a function? The thing inside it here? It has a name, a general name. Anyone remember hearing the argument of the function? This is the argument of the function. So we're going to do 1 over the square root of 1 minus this argument squared. So xy squared squared. Are we done on the left-hand side? No. Now what we have to do is multiply times the derivative of what's in here, which is going to require us to do what? Product rule. Product rule, right? Because we have a product right there. So we have to do the derivative of this one times this one plus the derivative of this one times this one. Always keep in mind that derivative of x is 1, derivative of y is y prime. So derivative of x, 1 times y squared plus derivative of y squared, which is 2y y prime times x. That finishes off the product rule, doesn't it? For that side. Parentheses. Are these parentheses necessary? Absolutely, because this expression would have to distribute through to both of those, wouldn't they? If I was going to free these things up from the parentheses, that would have to get distributed through to both. Leaving this off is a disaster, right? So there. Equals. Now, the right side. We have addition separating two terms, so we can do each derivative separately. Derivative of 1, 0, right? Plus, what do we need to do here? Another product rule. So the derivative of x, which is 1 times y, plus the derivative of y, y prime, times x. And that would be your derivative. Now, what would you have to do to get your y prime by itself on one side? This to here, this to here. So it looks something like this. Y squared over root 1 minus xy squared squared plus 2y y prime x over that same root equals y plus y prime x. So all that did was this thing appeared below each of those, right? That's it. And now you have a y prime term here. Bless you. And a y prime term here. So you're going to move those to one side, right? By what? Subtracting this one, bringing it over. Taking this y, bringing it to the other side, so subtracting it. Once you do that, what do? After you've got all your y primes over here? Simplify it, right? So you pull a y prime out, and then you bring all that junk to the other side. So look, this is Cal 1, right? The only difference is that now we are allowed to play with inverse trig functions too. Those can be part of our derivatives. I'll stop here. I want to get to this last example. We've got about 8 minutes. Let's see if I can wrap this up. Did the sign-in sheet get around to everybody? No? Okay. You'll hopefully recognize this problem. It's a related rate problem in Cal 1. A rocket is fired straight up with the speed of 1,000 miles per hour. So it's moving, okay, constant speed, 1,000 miles per hour. An observer who is a mile away from the launch point is tracking the rocket with binoculars. At the moment the rocket is 3 miles high, how fast is the observer's angle of inclination changing? What is that in degrees per second? So you basically have some guy standing there with binoculars on the ground. A mile away is a launch pad. He's looking at the rocket. The rocket is fired. We're assuming there's no acceleration. It's just instantly at 1,000 miles per hour, okay? So there it is, 1,000 miles per hour. He's following it with his binoculars. Exactly when the rocket is 3 miles high, we want to know how fast he's having to turn his binoculars to keep up with the rocket. Understand the question? Okay, so let's draw it with a picture. Here's my binoculars guy. That's my man standing on the ground. Okay, it's pretty impressive, isn't it? Here's my rocket. This is the launch pad. My rocket has been launched into the air. Here's my rocket. Flames. Again, impressive. I know. I get told that all the time. I'm in the wrong business here. All right, so I'm looking for angle of inclination. So if we're assuming that the guy's looking at the rocket, and we're going to look at the rocket as being a point, right? Then we're trying to figure out this angle and how fast it's changing, right? So depending on how you did, and again, how you were taught to do related rate problems, that's going to impact whether or not what I do up here is going to help you or like confuse you. I always tell my students with related rate problems to draw two pictures. One picture is a general picture. It's the picture of when things are moving. And then the other picture is a snapshot picture. It's the instant in time that's in question. So here's the first picture, calling this my general one. Is any of this ringing a bell? I mean, I'm getting some looks like this is the first time I've ever seen a word problem. Not sure if that's just... Are you all right? An instant in question. General picture, instant. What are the things, let's start with the instant one. What are the things that are definitely fixed, not moving at the instant in time? What can I assign values to here? I got what? 3 miles high and 1 mile high. So it's not drawn to scale. Sorry. Right? That's okay. It's still a right triangle. Those two sides are fixed. All right? How about this angle in here? Is it fixed right now in this picture?
Yes, we don't know it.
We don't know it right offhand, but yes, this is an angle, and I'm going to put a little check. I know what that is. In fact, I could find it easily. I could use the fact that tangent theta is 3 over 1, which is the same as tangent theta is 3. Right? And I could take arctangent on both sides and get my calculator out, and I could tell you what theta is. Couldn't I? Yes?
Yes.
All right, so I've got theta here. Here's my general picture. Anything over here that's not changing? A mile away. That's it, right? Is this changing in this picture? Yes. So since it's changing, I can't fix it at 3. I'm going to give it a variable. I'm going to call it y, only because we like x to be horizontal, y to be vertical. That's just a convention we like using. All right, so that's the picture when everything's moving. Is theta moving here? Is theta changing?
Yes.
Yes. All right, so now you try and write down what it is that you want. and what it is that you're given. So can anyone help me with this? Either one of these, what I want, what I'm given.
You want the rate of fast rate?
I want the rate that, okay, so, no, you know how to say it. You want the rate at which what?
The angle's increasing.
The angle that we're calling
Theta.
theta. You want to know how fast theta is changing?
Yes.
With respect to time, right?
Right.
So we want d theta dt. That's what we want. Now, start to ring bell?
There you go.
Okay. What are we given? Are we given the rate that something's changing? The speed, which represents which variable over here? Y, right? It's this distance, right? How fast is y changing? At 1,000 miles per hour. So we're given dy dt is 1,000, right? Also, what we wanted was d theta dt, but we didn't want it just at any time. We wanted it at a specific point. We wanted it when?
It's 3 miles.
When what was 3 miles?
When the rocket's 3 miles.
Which is what variable to us? Y. When y is 3. So that's pretty much the setup. You draw a picture of everything moving. You draw a picture at that snapshot, that instant in time. You try and figure out what it is you're looking for, when you wanted it. You're trying to figure out also what you were given. Once you have those, you have to try and connect this variable to this variable with an equation. Any equation you can come up with, looking off of this picture, not this one. What is an equation that relates these two together? Theta and y. I didn't hear. Can anyone connect y and theta together? Sine? Sine would be, we would need the hypotenuse, wouldn't we? Which we don't know. But tangent uses y and 1's not changing, right? So I could use the equation tangent of theta is y. Yes? And then what do? Once you find an equation, take the derivative with respect to time, right? Implicit differentiation with respect to time. This is what you would do in Cal 1. And that's fine. That's the same thing we're going to do here. The only difference is, what was it we were trying to find? Look, d theta dt, right? Theta's trapped in a tangent, isn't it? I can make this problem a lot easier for myself, if I release theta from the tangent. And to do that, I can take arctangent on both sides. And I'm going to do that before I take a derivative. So I'm just going to take arctangent of tangent and then equals arctangent of y. You okay with that? So that just leaves me theta